Hello and welcome. This is the pre-calculus fall final exam video review, and I'm going to be covering the following general topics here. Anything on functions, polynomials up to, cubics, quartics, etc., exponents and logarithms, and some trigonometry. There are going to be two sections to this thing. One's going to be non-calculator based, and one's going to be calculator based. So the way I'm going to go through this thing, I can't promise a whole bunch of speed. I'm going to try with some speed, and the way that I'm going to go about this is kind of as a student taking this. And what I mean by that is I'm not going to necessarily reteach things. Instead, I'm going to kind of just do the steps. But when I go through the steps, I will speak out loud what goes in my head, if that makes sense. So I'm going to be thinking my words out loud. And I think that that's going to be an important concept of stuff. So I won't necessarily say any misconceptions and whatever else. However, what I will also do is treat this as much as the non-calculator based stuff I'm going to do without a calculator. Graphing calculator stuff I can do with a calculator, so whenever I have to, I will use it. Now, I haven't done these problems before, so that's another thing. I might, not that I should, but if I struggled through something, it would be a legitimate struggle. And I'm also going to refer to my own answer key and see if I can match the answers as well before I move on. So, here we go. Number 1, evaluate each function. If k of x is equal to 4x plus 2, find k of 1. 1 is going to take place of x here, so I will get k of 1 equals 4 times 1 plus 2. 4 times 1 is 4. 4 plus 2 is 6. So k of 1 equals 6. On a graph, that means there's a point that is 1, 6 for this equation. Number 2, p of t equals negative 3 times 5 to the t power plus 1. Find p of negative 1. P of negative 1 is going to take place of t here. I have negative 3 times 5 to the negative first power plus 1. Negative 3 can't multiply with 5 until 5 gets raised to the negative first power here. So it'll be negative 3 times 1 over 5 to the positive first power plus 1. Negative 3 is negative 3 over 1. Negative 3 times 1 is negative 3. 5 to the first is 5. 1 times 5 is 5. That's negative 3/5 plus 1. 1 can be rewritten as 5/5. I was going to put 3/3. 5/5. Keep the denominator, add the numerator. Negative 3 plus 5 is positive 2. So you get positive 2/5 or 0.4. Let me confirm these answers are correct. All right, looks good so far. Number 3, perform the indicated operation. Start with number 3. G of t equals t cubed minus 2t squared. F of t equals 2t plus 1. Let's find g minus f of t. G minus f of t is g of t minus f of t. G of t very specifically is t cubed minus 2t squared. I'm going to wrap this around parentheses for no other reason than just to make sure that I understand that is g of t. F of t right here is 2t plus 1. The parentheses here will be incredibly important because when I subtract, I have to subtract the entire quantity. So this will be t cubed minus 2t squared minus 2t minus 1. Negative applies to both of those guys right there. Nothing combines. Looks like that's it. Number 4, f of t equals t squared minus 3. G of t equals 3t plus 3. Find f of g of t. This can also be rewritten as f of g of t. By that, we mean take g of t first and apply the function of whatever that value is. So g of t is 3t plus 3. Let's find f of 3t plus 3, which means 3t plus 3 takes place of t in f's equation. So f of 3t plus 3 would be 3t plus 3, quantity squared, minus 3. 3t plus 3 squared is 3t plus 3 times 3t plus 3. It is not 3t squared plus 3 squared. If you distribute, or if I distribute, I'll get 9t squared plus 9t plus 9t, that's plus 18t, plus 3 times 3 is 9. There's a lot of 3's and t's and pluses. Minus 3, which is 9t squared, plus 18t, plus 6. Confirmed. Okay, let's move on. Number 5, find the inverse of each function. F of x equals negative 15 plus 6x all over 5. F of x is also y, so I can write this as y equals. To find the inverse of a function, every x swaps with y and every y swaps with x. In this case, I only have one y and one x, so both of those guys will swap here. So it'll be x equals. Now, when I want to write the inverse function, the inverse of the function, I want to have it say some sort of y equals. My end result's going to say inverse function of x equals. So now I need to solve for y here the rest of the way after the swap. I have now taken the inverse. Now I need to kind of solve for that inverse. So in solving for y, I'm going to begin by multiplying both sides by 5. That will get the 5 out of the denominator, and I can continue to keep isolating y. 5x equals negative 15 plus 6y. Add 15 to both sides. Now I'm going to move the 6y over here, actually. Adding 15 to both sides, we'll get 5x plus 15. Divide everything by 6, we'll get y equals, or inverse function of x equals 5x plus 15, all divided by 6. Like so. If you're curious to write it in slope-intercept form, it would become 5/6 x plus 15 over 6. 15 over 6 can reduce to 5 over 2. So you could also write it like that as well. The first one is what's written in the answer key. Number 6, g of x equals the opposite of 3 over quantity x plus 1, all minus 3. Y equals g of x. So y is this guy right here. I'm going to swap x and y like I did last time. X takes y's place, y takes x's place. Put this negative specifically with the 3 up top here, just so you don't confuse the fact that it doesn't apply to both the top and the bottom, just to one of them. So there's that right there. Let's start solving for y. I'll begin by adding this 3 over. I feel more comfortable doing that than not. X plus 3 equals negative 3 over y plus 1. Now I need to solve for y. I need to get it out of its denominator. Let's multiply both sides by y plus 1, which means this gets multiplied by y plus 1. And over here, y plus 1, obviously those go away. But I'm not going to distribute here. Remember, I'm trying to just solve for y. It's by itself right here. There's a multiple of x plus 3 that is in its way right now. Eventually, I'm just going to end up dividing by that. Y plus 1 times x plus 3 equals negative 3. Now let's divide both sides by x plus 3, because as you can see, that gets the x's on the other side. X plus 3, x plus 3. So now we have y plus 1 equals negative 3 over x plus 3. Subtract 1, we get y equals, or inverse function. Oh, sorry, inverse function is g this time, right? Inverse function of x equals the opposite of 3 over x plus 3 minus 1 after subtracting 1 there. Okay, and that's what the answer says as well. Let's keep moving on. Number 7, graph each equation. Y equals the absolute value of x minus 4 minus 1. Here what we're looking at is stretch factor of 1 out here. Identifying the vertex means what's the lowest or highest point we can get. That happens when you take the absolute value of 0. When x equals 4, you're going to be taking the absolute value of 0. When x is 4, you get 0 minus 1, which is negative 1. Your vertex is going to begin here at 4, negative 1. Every point hereafter that I choose for x will be considered as the distance from the vertex. So if I chose 5 for x, that's 1 away from the vertex. That's the value I'm going to take the absolute value of. Okay. Starting from here, I've already subtracted 1. In fact, I'm going to ignore this negative 1 now because I've already taken care of it. I'm kind of ignoring this negative 4 as well. I'm just looking at the absolute value of x, and then I'm multiplying it by 1, which is taking the absolute value of x. So let's choose values for x here. or sorry, not choose values for x, but let's move away from here. If I move 1 away, I'll be taking the absolute value of 1, which is 1. If I go 2 away, I'll be taking the absolute value of 2, which is 2. Okay, I can't go any further. You can on your graph, but I can't plot any more points. Let's go the negative direction. If I go negative 1 over, the absolute value of negative 1 is still 1. And the absolute value of negative 2 is 2. And this keeps going this way, just like that. Negative 3 is 3. Absolute value of negative 4 is 4. So on and so on. And whenever I'm saying those values, again, I'm not plugging them in for the real x. It's kind of my new x that I created in that equation. Everything's based on where my vertex is when I create that equation. Remember, I've already subtracted 1, and 4 is already being considered because I'm over here. There's your graph. Identify the vertex and axis of symmetry, and hey, it doesn't hurt to graph as well. Y equals 3 times x squared minus 6. If I'm really not content on the look of this equation, I could write it into vertex form. Maybe I say, hey, I need to know exactly what my vertex is. X squared is also x minus 0 squared. So my vertex, just like last time here, the value of x that gives you 0 inside here is 0. When you plug in 0, you get negative 6 for y. So my vertex is going to be right down here. Now this is a quadratic equation. I have now taken care of my vertex points because everything's going to be in relation to that specific thing. And I'll be multiplying, I'll be squaring x, and any value I'll be multiplying it by 3. So I'm kind of looking at this equation here, y equals 3x squared, if my origin was down here. So let's take a look at that. If I go over 1, 1 squared is 1, times 3 is 3, 2, 3. If I go over 2, 2 squared is 4. 4 times 3 is 12. Now it's going up 3 squared, etc. will be a little too far now. So I could start going on the other side. For instance, if I go over negative 1, negative 1 squared is still 1, times 3 is 3. If you'd like, you don't have to do those specific calculations anymore. I'm not going to, because this axis of symmetry states that every point on the same height is reflecting the same distance away from this axis of symmetry. The other reason I'm talking about that is because I need to locate what it is. I could have located this axis of symmetry, by the way. It would be right there at x equals 4. This one's at x equals 0. If this at this height is 2 units away, this at this height is also 2 units away right there. Let's get the best looking graph that I can possibly get, and not even close. But parabola, curved up, should probably look a little more like that. There we go. My axis of symmetry is this line, not a curve. I'm sorry, not a point. It's a line, x equals 0. This one, once again, would be x equals 4. It's the line that determines where the points reflect across. And not every kind of graph has them. These two do. Okay, sketch the graph of each function. I got a couple more here. Square root function. 3 times the square root of x minus 4. This has a domain restriction, and this one's important, I guess, for me to look at. I know that I cannot take the square root of a negative number and have that located on a graph. So I have to make sure that all the values I plug in the square root are greater than or equal to 0. This is my domain. And not only that, this acts as a good starting point. I don't know if I can call it a vertex, but when x equals 0, I'll call it a vertex. When x equals 0, square root of 0 is 0 times 3 is 0 minus 4 is negative 4. Y is negative 4. So here's a good starting point for me right here. I could have also rewritten this as this if it's helpful, because some people like seeing this thing as the opposite, so they say. I don't like saying that, but the value of x that gives me 0 here is 0. Okay, now that I'm here, this negative 4 can be ignored because now I'm starting negative 4 down. So now I'm really looking at graphing this right here. I want to plug in values for x that's going to give me good values for y, like integer values. So let's plug in perfect squares for x. I've already plugged in 0. Let's plug in 1. Square root of 1 is 1, times 3 is 3. I don't want to plug in the square root of 2 or the square root of 3. Square root of 4 is 2, times 3 is 6. No square root of 5, 6, 7, or 8. Square root of 9 is 3, times 3 is 9. So it's up there. This graph just keeps going this way. It cannot go to the left. It will not go underneath as well. It is just a positive square root function, like that. Keeps going. Okay, number 10 is a lot of business going on here. What we have is a rational function. What I already know off the top of my head is that because this is a cubic divided by a quadratic, my result will be linear. So I do expect a slant asymptote. If I had quadratic divided by quadratic, I would expect a constant, so a horizontal asymptote. The other thing is that I have a quadratic in the denominator, so it is likely or possible that I will be looking at two vertical asymptotes, but we'll see what comes out of this here. Let's begin with the vertical asymptotes, or the potential ones right here. Vertical asymptotes appear when your denominator is 0, the values of x when your denominator is 0, if you're dividing a non-zero number by 0. So let's see, 4x squared minus 12x equals 0. If I factor out a 4x, I'm left with x minus 3, and that's equal to 0. Zero product property states if this times this equals 0, either this equals 0 or this equals 0. If 4x equals 0, then x equals 0. And if x minus 3 equals 0, then x equals 3. So my vertical asymptotes that I'm going to be referring to in this case, unless anything changes here, is x equals 0 and x equals 3. Those are the two lines that you will not get any points for this regardless. Here we go. I'll get in the slant asymptote later because this is a good setup to get me the x and y intercepts now. Let's go for y-intercept. The y-intercept is found by setting x equal to 0. So I can do f of 0 equals 0 cubed plus 0 squared minus 2 times 0. How fascinating of a problem so far. Over 4 times 0 squared minus 12 times 0. So that is 0 over 0, which is called an indeterminate. Now, an indeterminate is also not a point. This is not 0. This is basically nothing. There are no points there. And that should make sense, plugging in x for 0, not getting a y value out, because as we see, this represented a vertical asymptote. But what I know right now is that when I did try and find my y-intercept and such, I did get 0 over 0. And you're going to notice this one more time with x-intercepts and such. If you get a y-intercept, if you get a 0 over 0, in this case here, you're not looking at an asymptote there, you're looking at a hole. So we're going to take a moment and see that hole in a bit after we start plugging in some points. So there is no y-intercept. It cannot cross the y-axis. It will cross it. It will not touch it. It will jump it. The x-intercept is setting y equal to 0. So 0 equals, and I have x cubed plus x squared minus 12x. Now I could spend time writing over 4x squared plus 12x, but this will be largely irrelevant with regards to the problem itself. The reason is, oh, I'm sorry, this is minus 2x on top. 1 second. Thought something looked fishy. The reason is because I'm not trying to find the values of x that give me 0 on bottom. That's exactly the opposite of what I'm trying to find. I do have to be consciously aware of, if I get a value for x that it doesn't give me 0 in the denominator, you can already see one that's going to give you that. So we already know an x-intercept. But outside of that, I'm really looking at the top being 0. It's my important thing here. So I'm going to begin. I have a common factor of x that I can take out of here. So I have x squared plus x minus 2. This is equal to 0. Zero product property states either x equals 0, which as we know it cannot equal, but I'll leave that there, or x squared plus x minus 2 equals 0. If that's the case, let's keep factoring. This becomes x plus 2 times x minus 1 equals 0. If x plus 2 times x minus 1 equals 0, either x plus 2 equals 0 or x minus 1 equals 0. If x plus 2 equals 0, then x equals negative 2. And if x minus 1 equals 0, then x equals 1. Now, x equals 0, once again, did not work because when you substitute 0 for x, you end up dividing by 0 in the denominator. That one is an issue. We've already established that if you put in 0 or 3 in there, that would happen. Now, when you plug in 0, though, it's not just dividing by 0. It's dividing 0 by 0. So this is an indeterminate at x equals 0. And what you're looking at here is a hole, not a vertical asymptote. Therefore, this is also not a vertical asymptote. I know that's kind of strange, but vertical asymptotes appear when you divide a non-zero number by 0. When you divide 0 by 0, you're looking at a horizontal, at a hole. Okay, so features so far before I get anything else in play. I have this vertical asymptote. We'll take a look at that in a bit there. I have a hole there that it's going to be jumping through. And we have x-intercepts at -2 and 1, and we have no y-intercept. So x-intercept at -2 and 1, and there we are. Okay, let's try and find some more things. Now, like I said, there will be no slant asymptote, but I can find the other type of asymptote here just by dividing. And when it comes to dividing, I can use long division here. You cannot use synthetic unless this is a linear expression, unless it's a linear quantity, a linear factor. But I can factor an x out on top and an x out on bottom. And what your equation would look like if I factor those things out is f of x, because they would cancel then, right? This would be x times x squared plus x minus 2 over x times 4x minus 12. X over x is 1, and so now you're left with this. I'm also going to factor out that 4 for a moment. It's going to help me a little bit when it comes to long division, but it might require two different divisions. So I'm going to factor out this 4. This will be x minus 3 right here. So when I do division, I can do synthetic or long division. In fact, you know what? How about I do synthetic division now? But I'm just going to divide by x minus 3. After that, I'll divide by 4. So I'm going to move this 4 out of the way. The only reason is because I don't want to deal with fractions in that case right there. So this will be times 1/4. Whatever I get as a result, I'll just multiply by 1/4. That sounds fair. Okay, synthetic division. The root of this factor is 3. Quadratic term, linear term, constant term can line up right there. Let's start multiplying these things away. 3 times 1 is 3. Here's 4. 3 times 4 is 12. Negative 2 plus 12 is 10. The result that I'm getting right here is a rewrite of this function, the original function right here, or this one right here. It's being rewritten as x plus 1/4 times x plus 4 plus the remainder, 10 over x minus 3. Now, if I distribute this 1/4 into everything here, it's going to be rewritten as 1/4 x plus 1 plus 10 over, remember 4 is going to multiply with x minus 3, that'll be 4x minus 12 all over again. Okay, here is this thing after I divide. Now what this allows me to do is identify this quotient as the asymptote, the other type. This one specifically is a slant asymptote because this is a linear equation, a linear quotient, not a constant one. So your slant asymptote is at y equals 1/4 x plus 1, like so. Okay. The reason that this asymptote is as it is because you're always going to be adding or subtracting some value from it, because this can never be 0. It's impossible to divide 10 by a number to give me 0, so as x gets incredibly large or incredibly small, like incredibly negative, these numbers will get really close to here. Whatever the value of x is gives you a value of y, but it will never be that one. So let's take a look at that line, 1/4 x plus 1. Make sure it's plus 1. Plus 1 here. That'll be for my slant asymptote. Here's plus 1. Here's 1/4 x. I'm going to stretch it the other way. So I'm looking at a slant asymptote that looks like that right there. Okay, so now we have some points. We got to figure out kind of the rest of what's going on here. And by the way, this might not necessarily be at 0, 0, but I do know there's a hole here. I'll show you the left and right hand limit of this hole in just a moment. Let's do this in blue. Okay, now we got to start picking some points here that's going to help you determine where this graph kind of goes. Especially when it deals with cubics and quadratics, it can be a little tough. One thing that you can kind of see for sure is that this graph starts to be approaching underneath this guy right here. You could pick some points out. You can take my word for that there for now. This one's going to be approaching downward. So now the question's going to be, whether this graph is, can't quite do that, whether this graph is going over here or over here. And that happens by testing some points. And you don't necessarily need to get the final value because we know it's going to be approaching on those sides. What we don't know is which side of this asymptote it's going to be on. If it's underneath the slant asymptote, that means that you take this 1/4 x plus 1 and you'll be subtracting a number, meaning your remainder will be negative. If it's going to be above the slant asymptote, that means it's a number greater than 1/4 x plus 1, meaning you take 1/4 x plus 1 and you add a positive number here. So your remainder is positive. So let's test a value outside of this area. How about 10? Substitute 10 for x. Let's see if we are above or below the slant asymptote. 10 for x gives you, and not the exact value, but 10 for x gives you some number here plus 10 over 40 minus 12. 40 minus 12 is a positive result, so your remainder is positive. If your remainder is positive, then your point is above the slant asymptote. If your point is above the slant asymptote, so are all of the rest of them. So they're going to be approaching in this fashion right here. Again, I'm not going to be calling out specific points right now. I want to get the behavior of the graph in. You can plug in as many points as you'd like. Try your best with the fractions that you're given. Now, what's happening to the left and right of this hole? I am curious to see where this hole actually is. So here, if I substitute 0 for x, I will get an actual value. This is not a value for y that I can obtain, but this represents where the hole is going to be because I divided 0 by 0. So this is going to become 1 plus 10 over negative 12, which is 1 minus 5 over 6, which is 1 over 6. So your hole appears at 1 over 6, so for y. Okay, it's not a point on the graph, but it appears just above the origin right there. So the rest of the graph kind of connects and makes sense with that right there. I get these points. Okay, let me check. I haven't looked at the answer key. I'm going to look right now. Hang on. Number 1, 10. Yep, that looks fair enough. That looks like our graph. Okay, there's number 10. Okay, simplify. We've got a lot of imaginaries here to deal with. In terms of simplification, the following things must be applied. I'm looking to have no imaginaries in the denominator. I want to be in the form a plus bi, which also means a couple things. Only 2 terms maximum. No I squareds, I cubes, anything like that. And these 2 terms completely split apart. The real component and the imaginary component have nothing in common, meaning I don't want to even be all divided by the same value. I'd rather split them up like that. All right, here we go. Here's a complex number, negative 6 minus 5i, and here's negative 6 minus 3i. Let's add those two. It'll be helpful to just, combine like terms, real ones with imaginaries. Negative 6 plus negative 6 will be together. Negative 5i plus negative 3i will be together. This is negative 6 minus 6, minus 5i minus 3i. Can't stop being negative. That's negative 12 minus 8i. And that's it. There's no distribution. That's addition. This one is distribution. We have negative 2 times 6, negative 2 times negative I, 8i times 6, and 8i times negative I. Negative 2 times 6 is negative 12. Negative 2 times negative I is positive 2i. 6i times 8i is 48i. And 8i times negative I is negative 8i squared. Well, I squared happens to be negative 1. Okay, the whole idea is that I is the square root of negative 1. Okay, that's why we bother doing this business in the first place, using I instead of square roots of negatives. So I squared is negative 1. So here, this is negative 8 times negative 1. So I have negative 12 plus 50i. Negative 8 times negative 1 is positive 8, so plus 8. Negative 12 plus 8 is negative 4. So I'm left with negative 4 plus 50i. Okay. Number 13, 9 over 8 minus 6i. Now, my intent is not to do division like synthetic division, whatever. Especially if my result ends up in a remainder and I'm still dividing by 8 minus 6i. The whole plan is just to get this thing in a plus bi form. That's all I want. And no imaginaries in the denominator. So I have an imaginary in the denominator. I want to get rid of it. The best way to get rid of it is to take any sort of a plus bi value and multiply it by its complex conjugate, which is written as a minus bi. this end result, if you distribute everything, you will get a form a squared plus b squared, which means it'll be the real component squared and then the imaginary coefficient squared, and those two added together. Now, I can't just multiply it by the bottom because then I'm changing my value. I will do it by the bottom, but then I also must do it by the top. Again, I have to multiply by 1. You know, I can't change this value, so I'm multiplying by 1, but I'm re-representing it, right? So 8 minus 6i times 8 plus 6i becomes, in general, it does simplify to 8 squared plus 6 squared. It's those two values, your a and your b. So 8 squared plus 6 squared. On top here, I can distribute the 9 into the 8 and the 6i. So 9 times 8, whoops. 9 times 8, 9 times 6i. 9 times 8 is 72. 9 times 6i is 54i. Okay, 8 squared is 64. 6 squared is 36. Sorry. And then 64 plus 36 is 100. So I have 72 plus 54i over 100. All those look like 9s. And like I said, I want to split these components apart completely. So this will be 72 over 100 plus 54 over 100. 54i over 100. Both of these are at least even numbers, so this can simplify a couple different ways here. This is actually even divisible, I think, by 4. 72 divided by 4 is, oh boy, it's 18? 18? I think it's 18. 18 over 25. That's as much as that one can reduce there. You can write these as decimals, 0.72 and 0.54. I guess that'll work. But, you know, simplify this however possible. 54 divided by 2 is 27, so we can do 27 over 50, 27i over 50. I think that's as small as I can get both of those. But like I said, this can also be written as 0.72 plus 0.54i exactly here or here. Let's see what the answer key says. Number 13. Okay, so for number 13, they did reduce this as one fraction. I would prefer not to, but if this is in the multiple choice, understand that, you know, because I do want to follow the key now, understand that all of these can divide by 2. Remember I divided this one by 4? That also means I could divide it by 2. So if everything divides by 2, meaning you factor a 2 out on top, and you factor a 2 out on bottom, you're just left with 36 plus 27i all over 50. Like that. So all of these are equivalents. If you see any of these on a multiple choice test, those are all the same answer. Okay, number 15 is more of the same here. I have an imaginary in the denominator. Remember, this is 0 minus 6i. If that helps you understand what its conjugate is, 0 minus 6i is here. We're going to multiply this by 0 plus 6i, or better yet, 6i. So let's multiply top and bottom here by 6i. Okay, and now I could do negative 6i. It's still going to give me a real number, but you know, just be very cautious of the fact that complex conjugates are probably the best source of this stuff. 6i is going to multiply with both negative 7 and negative 7i. On the bottom, by the way, negative 6i times 6i is negative 36i squared, which is negative 36 times negative 1, which is positive 36. On the top, negative 7 times 6i is negative 42i. Negative 7i times 6i is negative 42i squared. Whoops. Negative 42. Like that. Okay. Negative 42i squared is negative 42 times negative 1, so it's positive 42. I'm going to write that in front. Positive 42 minus 42i over 36. I can factor 6 out of all these, so 6's can cancel. I'll be left with 7 minus 7i all over 6. I'm sure this is the answer they have on that answer key. If you did split it up, it'd be 7 over 6 minus 7i over 6, or 7 over 6i, like that. Either or, let's see. Oh, wait, where's I skipped number 14. Oh, 14's on the next page. My apologies. This is 13, this is 15. Yeah, so the first one, they have negative 7i written first. All that stuff is the same. Okay, number 14 was a different kind of problem. That's why I think I wrote it next after this. Graph the number in the complex plane. The real plane is 1, 2, 3, 4, negative 1, negative 2, etc. This has 1i, 2i, 3i, and negative 1i, negative 2i, negative 3i, etc. This is as simple as saying let's go 2 to the left in the real direction, 2 down in the imaginary direction. There's your point. That's negative 2 minus 2i. That's it. Number 16, state possible rational zeros for each function, then find all zeros. Possible rational zeros, possible rational zeros in this case here, I'm going to take all factors of this number here, and I'm going to call those numbers p. And I'm going to take all factors of this number right here, and I'm going to call those factors q. Now, there aren't too many to speak of. P are possible p's over q's. All your factors of 11 are positive negative 1, positive negative 11. All your factors of 1 are positive negative 1. So your total sets that you're looking for, there's 1, negative 1, 11, and negative 11. These are the only possible rational zeros in this set. Excuse me. So to find all the zeros here, it means we have to solve for x, right? We have to set this guy equal to 0 here. And we have to determine which ones will pan out for us. Now, what I do see here is that it would be impossible for me to have any positive x's as answers. The reason being is all of these values here are positive. If every single one of these is positive and you put positive numbers in here, they're just going to become larger positive numbers. So it's going to be impossible for these to reach 0 unless I'm looking at negative 1 or negative 11. I'm going to test negative 1 first and see if I get 0 there. So f of negative 1. If I do, then I'm just going to use that. Negative 1 cubed is negative 1. Negative 1 squared is 1 times 13 is 13. Negative 1 plus 13 is 12. Negative 1 times 23 is negative 23. 12 minus 23 is negative 11. Negative 11 plus 11 is 0. So negative 1 checks out. This is one of my roots. If this is one of my roots, then x plus 1 is one of my factors. If x plus 1 is one of my factors, then I can divide this polynomial by this factor. And I'm going to use synthetic division for it, so I'll be using the root negative 1, but I'm explaining what it is I'll be dividing out. I'll be dividing this by x plus 1 so I can be left with a quadratic. If I'm left with a quadratic, then I can solve it in any way which I prefer. If it's factorable, I'll do that. If not, I can use quadratic formula or completing the square. Now, we already know that we should be getting a 0 remainder out from here if your remainder is equivalent to the y value you get out by substituting in your value. So I could have done this from the beginning, but this might take longer for people instead of shorter. Anyway, when I divide everything by x plus 1, so my function now looks like, by the way, x plus 1 times this guy, x squared plus 12x plus 11. Okay? This is factorable. By the way, I'm setting this equal to 0 now, right? This is x plus 1 times x plus 11 times x plus 1. So it looks like I have x plus 1 quantity squared there. That's not necessarily important, but I can speak on multiplicities if you're curious. And x plus 1 equals 0, so x equals negative 1. This has a multiplicity of 2. Not necessarily important for the sake of this problem, but if it does show up on the answer key, I want to make sure to explain away that it's because of this 2 here, this has a multiplicity of 2. X plus 11 equals 0, so x equals negative 11. And what's interesting is, it looks like I could have tested this one to see if that would have been my other answer there, and I would have been right. I wouldn't have known the multiplicities necessarily, but your only possible rational values are also your only solutions to this problem. Negative 1 and negative 11. There were no imaginaries or irrationals whatsoever. It was actually the 2 in the list right there. But I only used one of them first to divide it out, get it into a quadratic, and do something from there. Yeah, you don't have to divide if there are other special cases, such as factoring by grouping, or something here where you can turn this into a special quadratic. And I'm about to do that. First, let me look at the answer here. Okay, yep, so they have the possible rational zeros listed here. And then they have negative 1 with a multiplicity of 2 and negative 11. Okay, find all zeros. They do not say state possible rational zeros. If they did, though, because you want to know how that works there, your possible p-values, and by the way, this is a way that you can solve it, right? So your p over q's, you can do plus or minus 1, plus or minus 2, plus or minus 3, or plus or minus 6. Like that. All over plus or minus 1. Those are your factors of q. Let's change the color here to not conflict with that problem. Okay. So your possible values are any of those. 1, -1, 2, -2, 3, -3, or 6, -6. And keep in mind, only negatives look like they would be able to go in, because as you set this equal to 0, only negatives would even possibly give you that. And actually, as I look at this right now, negatives won't either. -1 to the 4th power is positive 1. Or, you know, negatives to an even power is a positive number. I don't think any of these will work. So you have to find another method completely. Yeah, I'm just saving you time there. Now, what I'm going to do here, I recognize that these degrees descend by the same multiple. They're descending by 2 all the way down to the constant. That means that I can almost treat this thing like x squared quantity squared if this is x squared to the 1st power, and this here is 6. Notice how the x squared is squared. This x squared is to the 1st, and this is 6. So this is like a quadratic in itself. If this looks a little confusing, feel free to assign a temporary variable. I always use the letter u. You're going to be using that a lot in calculus as well. Let u equal x squared, and this temporary variable gives you the better perception of what kind of problem this one here is. So it looks like that in the end, u squared plus 5u plus 6. That can factor to u plus 2 times u plus 3. Okay? Okay, now we have to solve for x still, though. So u was equal to x squared. Those were equivalents. I used u to help me factor. I am now finished with using u. Thank you, u. And plugging this thing back in. Remember, we're trying to find the values of x when y equals 0. So setting this equal to 0 allows me to use zero product property at this point. Either x squared plus 2 equals 0 or x squared plus 3 equals 0. So either x squared equals -2, in which case x is plus or minus the square root of -2, which is plus or minus I root 2. Or x squared equals -3, in which case x is plus or minus the square root of -3, or x equals plus or minus I root 3. So you can see you have imaginary sets right here. And of course, they are complex conjugates of one another, like so. To get real coefficients out, not only that, but integer coefficients, I had to have complex conjugates. Positive I root 2, negative I root 2. Positive I root 3, negative I root 3. Let's see our answer. Yep, that's the set. And the set's written out in curly braces like this. So when they write something out in curly braces, that's representing the entire solution set for x, like so. Okay, that's the same thing as what this says. It has to be in curly braces, though. You write it in parentheses, you're representing something else. Square brackets, you're representing something else. So you can write it like that as well. Okay. Okay. Graph each function. We have another set just like that last one. Let's see if I can do this a lot more quickly based on having spoken through the other one. Let's start with vertical asymptotes here. Vertical asymptote is making sure that I don't divide by 0 here, so I have to find out those values of x that do give me 0. Okay. If I factor out a -4x, I'm left with x plus 1. So if -4x equals 0, then x is equal to 0. And if x plus 1 is equal to 0, then x is equal to -1. Okay, so these are possible vertical asymptotes, but like we saw last time, and it looks like we'll see it again here, x equals 0 might represent a whole. Okay, so vertical asymptotes, although of course this one might go away. It will go away, but okay, y-intercept. Setting x equal to 0. Now, as we know, we're going to get 0 over 0 here. Let's see it. 0 minus 0 minus 0 over 0 minus 0. So we get 0 over 0, which is an indeterminate, which is not a point. It will represent a hole. It might not necessarily be right at 0, 0, but we do know that a hole is going to be there. This is not a vertical asymptote. This is a hole. Okay? X-intercepts at y equal to 0. Now, once again, I'm going to be focused on the numerator. As I'm focused on the numerator, let's see, we got 0 equals x cubed minus 2x squared minus 3x. If I factor an x out, I'll have x squared minus 2x minus 3. So either x equals 0, which of course we know can't be the case. This one represents that same hole. Or x squared minus 2x minus 3 equals 0. In which case, as this is also factorable, we have x minus 3 times x plus 1 equals 0. So either x equals 3 or negative 1. These are my x-intercepts right here. So I have some features provided for me so far. 3 is an x-intercept. Negative 1 is an x-intercept. Negative 1's a hole. Here's another one. Negative 1 is an issue with this one as well. So it looks like we have no vertical asymptotes. Because again, if you plug in negative 1 into here, and I don't have to prove it. I think we just established that negative 1 will give you 0. This will become another issue there. So this problem, see, let's draw two little holes just to say, hey, there will be holes here. We don't know specifically where yet. We'll find them in just a moment. Now we can find them after we do some division. Here, I'm going to find that slant asymptote. Once again, it's going to be another slant because it's a cubic divided by a quadratic here. We know that you can factor out a couple of things. Okay, we know that on top there's an x plus 1 and on bottom there's x plus 1. That's what gives us 0 over 0. We know that on top there's a common factor of x and on bottom there's a common factor of x. So if I take f of x equals, on top this can become x times x plus 1 times x minus 3. We established that here. Okay, that's equivalent to this. On bottom, we established here this can become negative 4x times x plus 1. So look what cleans up. This is pretty nice. X over x is 0. It was 1. And x plus 1 over x plus 1 is 1. So our equation can also be rewritten as f of x equals x minus 3 all over negative 4, which can also be rewritten as negative 1/4 x plus 3/4. So your graph is nothing more. See, this isn't a rational function, really. It's not the same kind that we'd be looking at like before, right? This one is having some little differences here. This one just appears to be linear, but it just has some holes, right? It doesn't have any asymptotes. It's just looking like this right here. So what I can do now that I've divided and canceled out these guys here is I can find the value where those holes would have appeared by substituting in 0 for x right here and negative 1 for x right here. Okay, that'll give me the y location of my holes. So f of 0 is 0 plus 3/4, which is 3/4. Okay, f of negative 1 would be negative 1/4 times, what is it, a negative 1, plus 3/4, which is 1/4 plus 3/4, which is 1. So that's where my holes appear at negative 1, 1. Oh, these are attached. Hang on. At negative 1, positive 1, there's a hole. And then at 0, 3/4, there's a hole. Now, it's interesting that there's a hole at the y-intercept, but that's how we graph this thing. Graph it like any old linear equation. Start at 3/4, and you can go down 1 over 4 every time. It might be hard to do it from these ones here, because if you go down 1, you're down to negative 1/4 right here. So it's kind of hard to plot those points. What I can do is pick a point that I know that's on integers, and I can apply the slope there, down 1 over 4, like so. So I can go down 1 over 4. Here I can go up 1 over 4, hole, up 1 over 4, etc. So your graph, this will be a little broken apart here. One moment. There's your graph. You got two holes. It's a linear equation. There you are. Let's see what the answer was here. 18. Yep, 18 looks like it has that one right there. Linear, came through division. Dividing really helps realize what's there. Now, normally this would be your slant asymptote, right? But the reason why it's not a slant asymptote is because there's no remainder that's adding to it, like, plus 2 over x minus 7. There's nothing else that says that this will always be above or below this line here. That's why the asymptote normally exists. Okay, here we go. Moving on. Number 19, solve each equation. 2 to the 3x plus 3 power equals 1/2. What is the value for x that makes that true? The way that I'd probably look at this problem is say, first of all, 2 to what power gives you 1/2 in the first place? Right? We want to figure out what this whole thing is supposed to be to even get this. What I'm going to do is go for a matching base, same base principle, meaning I have 2 to the 3x plus 3 power here. And over here, can this be written as 2 to some power? And the answer is yes. This is 1 over 2 to the first power. This is 2 to the negative first power. Those are equivalent. If that's the case here, if 2 to this equals 2 to that, then this is equal to that, and we can therefore solve for x. If 3x plus 3 is negative 1, subtract 3, divide by 3, we'll get negative 4/3. And apparently that's the value of x that gives you everything that you need there, as you can probably double check. Okay, number 20 requires the same kinds of steps here. We want to get the same base on the left and right side. And if you know enough about 625, you know it can divide by 5. You could probably work from there and figure out how many times it divides by 5. But the square root of 625 is also 25. So this is 25 squared to the 3x power. Now that's helpful because now I have the same base on both sides, but I wouldn't yet set them equal to each other because I want to multiply this exponent with this exponent right here. 25 to the 2 times 3x is 25 to the 6x power. And then that's equal to this right here. Okay. Now you could solve the rest of the way and solve for x. Now if you didn't know that 625 is 25 squared, at least know that it divides by 5. Well, you should know it divides by 25 as well, right? But also know that it divides by 5. And you might say, all right, well, this is 5 times 125, boom, to the 3x power. And you'd keep working, and 125 divides by 5 as well. So you see this 25 times 25. So you get back to 25 squared. You can also put 5 to the 4th. Okay, you'll be approaching the same stuff. But if you get 5 to the 4th on the left side, then on the right side, you want this to have a matching base. So this would be 5 squared. And you'd be getting into the same work as before. Anyway, I'll work with this one right here. 6x is equal to negative 2x minus 3. Add 2x to both sides. Divide by 8. We get negative 3/8. The exact value for that is negative 0.375. And one or the other applies there. Number 21, sketch the graph of each function. Okay, so we are looking at an equation that is written in this form, y equals a times b to the x minus h power plus k. A and b can never multiply together until you raise b to this power, so I cannot begin by doing 1/4 times 1/2 is 1/8. This is not the same thing as 1/8 to the x power. Okay, so definitely different there. All of these values mean something. In fact, this one would be minus 0 over here and plus 0 right there. Not that those matter too much, but if you do know anything about these values, you can use them. And I will try and do the same by doing this. As x gets infinitely large, incredibly, incredibly large here, this 1/2 multiplies by itself so many times it gets so close to 0 that it might as well be 0. A number that might as well be 0 times 1/4 might as well also be 0. As x gets infinitely large, your points start to approach 0. Now 0, y equals 0, is the asymptote in this case here, because it never becomes 0 itself. Okay, so y equals 0. That is my asymptote. It will never touch those points. So close to it, though. And that will be equivalent to your k value. Your k value is your horizontal asymptote in this case. Okay. This 1/4. What will be helpful here, and look, you can plug in any point for x that you'd like, but if I substitute 0 for x, only because that gives me an exponent of 0, 1/2 to the 0 power is 1 times 1/4 is 1/4. So I know that that 1/4 will be when my exponent is 0. That's just right down there. which is not a great number. It is very, very small. Hopefully I can get larger numbers. As x continues to increase by 1, your y value continues to be half of what it was before, right? 1/4 times 1/2 to the first power is 1/4 times 1/2, which is 1/8. That's when x is 1. When x is 2, you get half of 1/8, which is 1/16. And 1/32, and so on. This is not a very pleasing graph, as you can tell. But if we keep multiplying by 1/2 or dividing by 2 going this way, then going to the left, we should be multiplying by 2 or dividing by 1/2. So 1/4 times 2 is 1/2. 1/2 times 2 is 1. 1 times 2 is 2. 4. 8. 16. Good thing they have numbers for these ones. And 32, and so on and so forth. So this is a decay, an exponential decay graph. Find whatever starting point that you'd like. It's great no matter what point you choose. As long as you can get that value for y, just understand how far it is from your asymptote. And every time x increases by 1, you multiply by your growth rate one more time than before. So I draw that half arrow there to represent infinite continuity that way, but it will never cross this asymptote right here. Okay, let's start looking at some log equation, or some log expressions and log equations in this case. Let's condense this expression to a single logarithm. Now, to make this one a little more useful, you can do one of two things. These are all divided by 2, so you may write them all over 2 as follows. Plus log base 3 of z all over 2. And all over 2 is the same thing as times 1/2. So 1/2 times this entire set. Okay, this is one way to go about it. Another way to go about it is to apply the 1/2 into each individual thing at the same time. But I'm just going to go ahead and use this one here. Now, I'm not going to apply that 1/2 just yet as an exponent inside my logs. Let's first condense these as one log. Then let's bring the 1/2 all up in there. So the sum of multiple logs is the log of the product of those inside values. So this should be 1/2 times log base 3 of x times y times z. Now this 1/2 is going to relocate. I'm going to bring it up into this guy right here, not just for z, but for x, y, and z. So if you raise all three of these to the 1/2 power, what is that equivalent to doing? Well, the answer is it's equivalent to taking the square root of them. So this equals log base 3 times, or times, great. Now I just said what a lot of other people say. Log base 3 of the square root of x times y times z. There you have it. So that's a fully condensed logarithm, taking care of the exponent and everything else. Depends on the order that you do it, but no matter what, you'll be there. Number 23, log base 7 of 4a minus 5 equals log base 7 of 3a. If both these logs have the same base and these guys are equal to each other, then the inside values have to be equal to each other. So 4a minus 5 equals 3a. This is true. This has to be true in this case. Subtract 3a, add 5, right? A equals 5. That was easy enough. One thing you want to be cautious, though, with log problems is just make sure that your value does work in your original set. Like if I substitute 5 into here, not saying make sure that both numbers work, but make sure that you don't take the log of a negative value or of 0. In this case, I'll be taking log base 7 of 15 equals log base 7 of 15. All's good. I have no issue there. Number 24, evaluate this guy, log base 4 of 16. I'm going to go ahead and set this equal to x because I want to convert this into exponential form to fully describe what it is I'm looking for. When you take the log of something, your result is an exponent. So this base raised to that exponent should give me 16. And I need to know what number that is. Well, it's 2. Right? 4 squared is 16. That's all you're trying to do for that problem. Just determine what it is, and if it's a non-calculator problem, it's probably something that you know how to square or change the bases so that they're the same. Okay, expand this logarithm now. All right, let's go and do that. Now this cube right here, the 3 power, this is inside the logarithmic function. So I'm going to put the brackets around there to make sure you know that. To begin this expansion, let's go ahead and let's take that 3 out. Multiply it in front of this log. That's 3 times log base 4 of 2 squared over 3. And you might be asking, should we square that? Well, as far as expansion goes, let's take everything out that we can, right? We might even be able to get some other values within this. Okay, division within a log means I can subtract, it can be a subtraction of 2 logs. So this will be 3 times that difference. 3 times log base 4 of 2 squared minus log base 4 of 3. Okay. As far as full expansion after that, you may distribute the 3. How about 3 times log base 4 of 2 squared minus 3 times log base 4 of 3. And finally, this 2 can now come out and multiply with the log in, of course, with the 3. 2 times 3 is 6, so we'll get 6 times log base 4 of 2 minus 3 times log base 4 of 3. If that's all I wanted for full expansion, that would be all that you'd be able to do. I can, CAN, I can continue with this, yes. 4 to some power does possibly give you 1/2, right? You can look for what that one is. It would be to the 1/2 power in this case here. So if it was 1/2, I could do 6 times 1/2 minus, and I don't know, 4 to what power gives me 3? I don't know. So I wouldn't be able to do anything with that. So basically, I could also write this as 3 minus 3 times the log base 4 of 3. So either or, I don't know which one the key actually gives. I actually do not have that key on hand anymore. But one of these two is acceptable as far as getting full expansion first before you do any other evaluations, should you be able to do so. Identify the domain and range of each and then sketch the graph. This is a logarithmic function here. All logs have an infinite set within their range. Their range is all real numbers. The domain is limited, though. Range is all real. Domain has issues when you take the log of 0 and of negative numbers. So this guy has to be greater than 0. If that's the case, x has to be greater than -1. Subtract 1 from both sides. You get that. X is greater than -1. So now that we know the domain, we also can understand, as far as this graph goes, where its vertical asymptote is. If x can be greater than -1 at any moment, then it can't be -1 or anything less than. -1 must be a barrier. This x equals -1 right here. And if that's the case, every other point on this graph is going to be to the right of this line. Okay. So here's how I'm going to work this thing here. Some people might look to plug in certain values for x. I can work with plugging in a first value for x. After that, I'm going to work with understanding inverse of exponential functions. And my starting point I'm going to choose the first one that's to the right here when x is 0. When x is 0, what I get inside is the log of 1. Log base 2 of 0 plus 1, right? Well, log of 1 is 0, no matter your base. So the good news is if I take the log of 1, this goes away, and then all that's left for y is just this constant value, 1. When x is 1 away from your vertical asymptote, your y value will be this k value right here. So there's a point on my graph. And if you were to choose values for x, say within a table, you had to make sure that you could raise 2 to some power to get the value inside here, x plus 1. Every value that you can take the log of cleanly with this 2 is a power of 2, such as 1, 2, 4, 8, 16, etc. Every time that x value is going to have to double, or the x plus 1 value is going to have to double what it previously was. So my x distances here are going to double their distance away every time my y value, my exponent, increases by 1. Remember, y is now the exponent. This is 1 unit away from the asymptote. As y increases by 1, your x value doubles. There's another point. You plug in 1 for x, you'll get 2 for y. You plug in, apparently, 3 for x, you'll get 3 for y. You plug in 7 for x, you'll get 4 for y, etc. So I'm kind of using y because y is the exponent, and that kind of helps me just say 2 to this power gives me this far out. And that's all I'm doing there. As I multiply by 2 going out this way, I will divide by 2 going down this way. So again, feel free to use a table as needed. Just make sure that you understand that you can't always use a calculator with it. So you got to know how logs work anyway. And you got to be picky about the points that you choose. It's probably easier to just think about what y values to choose. And you get the x plus 1 value in as a result. And there's a horrible looking graph. Number 27, use the properties of logarithms and the values below to find the logarithm indicated. Do not use a calculator to evaluate the logs. So if you're given this set of 3 things right here, and these are approximations of the actual logs, let's use these rounded values to find out what it is they want us to find out. Log base 8 of 9 is this. Log base 8 of 5 is this. Log base 8 of 12 is this. Let's find the log base 8 of 144. Okay. Now you might be sitting there going, I'm not sure what to do. One thing I would do is I would look at this as, are there any factors of 144 that are written inside here? 9 and 16 would be factors. 12 and 12 would also be factors. In fact, I think I want to try and play with the 9 and 16 one after this first set here. This is log base 8 of 12 times 12. You can also write that either as log base 8 of 12 plus log base 8 of 12, or log base 8 of 12 squared. Okay. Log base 8 of 12 squared, the 2 can come out in front and play, and multiply with log base 8 of 12. Now, do you know what log base 8 of 12 is? Not so important because they give you it right here, about 1.2. So this is 2 times 1.2, which is 2.4. Okay. That's one way of going about it. Let me try a second way. Again, I'm doing this for the first time, so let me try this a second way. Let's try log base 8 of the less popular factor, 9 times 16, which I can separate as log base 8 of 9, which we have an approximation for, by the way, plus log base 8 of 16. Okay. Log base 8 of 9 is about 1.1. Log base 8 of 16 asks you the question, 8 to what power gives you 16? Now, 8 can be re-represented as 2 cubed, whereas 16 can be re-represented as 2 to the 4th. 3 times x is 3x, so we get 2 to the 3x equals 2 to the 4th. So 3x equals 4, or x equals 4/3. So log base 8 of 16 is 4/3. That's the exponent you raise 8 to get that. Take the cube root and then to the 4th power. So 4/3, I'll just write plus 4/3. I'll get an approximation now in just a second. So that's about 1.1 plus, it's about 1.3 repeating, right? But if we're rounding to the nearest 10th, just like we did in the previous sets, 1.3. 1.1 plus 1.3 is 2.4. So I still get it there. Still get the same answer. That's kind of cool. It's fun to play with those a little bit. I didn't use log base 8 of 5. Is it there for any particular reason other than to stump you? Maybe. Maybe there were some more partial problems to try with it. But this one was not used, not needed. I'm trying to think if I can use it in a certain way. I don't know. Maybe not. Number 28. Oh, okay. Now we're looking at some trig stuff. Convert each degree measure into radians, negative 140 degrees. This will always help to just draw yourself a quick graph, okay, and understand what's happening here. Now, if you know proportionality, like I do, I'll show you that way as well. But what I might start by saying is, first of all, negative direction is clockwise. Here's 90 degrees, okay? 180 degrees is all the way here. Okay, 140 is less than that. Probably goes to about right there. All right, so this distance is negative 140 degrees. And we're trying to figure out what this degree measure is also in terms of radians here. So this drawing may not necessarily help you too much except for understanding where your radians should be in between. Just understanding what that measure is, or it can help you find a positive counterpart for that measure here. If negative 140 goes here, the positive version of that meaning 360 minus 140, which is 220, is what we can also convert this to. So this is also the same as 220 degrees. These are coterminal angles right here. And I'm going to convert 220 degrees into radians. I know that the answer sheet might have a negative answer here. I'm going to go ahead and give you the positive one. And I can subtract from 360 to give you the negative one as well. Okay, 220 degrees. So here's what's going to happen. We know that every 180 degrees in the circle, you are also going pi radians. So 180 is to pi as 220 is to some unknown radian measure that we just don't know. So there's your setup. That's what we're working with. Cross multiply 180 times that radian measure is 220 pi. Divide both sides by 180. We get r equals 220 pi over 180. Now, don't whip out the calculator just yet. In fact, start dividing this stuff. Both of these guys can divide by 20 on top and bottom, so that's going to give you 11 pi over 9. So this is the radian measure, the positive radian measure of what we had there. Now, if you wanted to give the negative version of what was there, in case that answer shows up in the either multiple choice or whatever it is you're talking about, do this number back, subtract 360 from it, or in this case, subtract 2 pi. 11 pi over 9 minus 2 pi, which by the way is 18 pi over 9, is equal to negative 7 pi over 9. So this is the exact radian measure that ties in with negative 140 degrees. Or the positive counterpart of that, the coterminal measure, is 11 pi over 9 positive. So one or the other, you're set. Okay, let's convert this one into degrees, and kind of going by the same concept here, same focus. I'll go straight into that proportion idea, but just understand that every single time that this thing is revolving around and around and around again, because it does it multiple times here. Well, shoot, I forgot what I was going to say on that. But every time you go around one full revolution, that's another 2 pi radians. Okay, but I can use this simple conversion right here with degrees and radians. 180 degrees is equivalent to pi radians, yeah? So 180 degrees is equivalent to pi radians, as some degree measure is equivalent to negative 199 pi over 36 radians. Okay? If you were looking to cross multiply, okay. Yeah, let's play with this a little bit here. We got 180 times negative 199 pi over 36 equals theta times pi. First of all, if you divide both sides by pi, they will cancel out on both sides. Pi over pi is 1, so those are gone. Second of all, don't start too much to be multiplying 180 by negative 199. You could, but I'll show you an even quicker measure to do that. But first, understand that 180 is also dividing by 36. Okay. Now 36, as I understand it, there's 36, 72, 108, 144, 180. 180 divided by 36 is 5. So this is 5 times negative 199. And that's equal to your measure. Okay. Now, again, don't go straight to the calculator or to multiplying this, by hand. This is the same thing as 5 times negative 200 plus 5 times 1. Negative 200 plus 1 is negative 199. 5 times negative 200 is negative 1,000. Plus 5 gives you negative 995 degrees. Now, this is an answer in degree, this is your this is your negative degree answer. We could get a positive degree answer, and we could get one between 0 and 360. So I'm going to work to both of those things. Let's start by figuring out how many times this goes around a circle. Okay, so let's check it out. I'm going to go back to here. I have negative 995 degrees, so I'm going a full 360, the clockwise direction, 720, and if I want a full another circle, I'd be going 1080. Now 1080 is more than 995. How much more? Well, 85 degrees more. So I would need another 85 degrees to get back to 0. So if this goes all the way up until about this point right here, you would need another 85 degrees to go the rest of the way, right? So this measure right here is 85 degrees. That is the equivalent to what it is that we're looking at right here. This and 85 degrees are both coterminal angles. Again, just go multiples of 360 as many times as you need to, and then you can land on that. Number 30, find the measure of this angle. Okay, so I assume that they're referring to the red right here, right? Let's call this thing R because it looks like it's a radian measure. So finding the measure of the angle requires knowing how many revolutions you're going around the circle. Looks like there's a full revolution, so for sure we're doing 2 pi. And then we're going to be adding a little bit more here. Another half circle is another pi. And then this amount right here is pi over 6. So we're going to add those 3 things. Now 2 pi is equivalent to 12 pi over 6. Pi is equivalent to 6 pi over 6. Now that I have a common denominator, I can add straight across. 12 pi plus 6 pi plus pi is 19 pi. This is all divided by 6. And that can't reduce anymore. That's the measure of that angle. If you want to convert to degrees, go ahead. This is equivalent to a full 360 plus another 180 plus pi over 6 is 30. So 360 plus 180 is 540 plus 30 is 570 degrees. If you want to do that first and then convert back into this, that's fine. Number 31, find a positive and a negative coterminal angle for each given angle. Just to restate what coterminal means one more time, 295 is somewhere, here's 90, 180, 270. 295 is 25 degrees more right there. So this guy's 295. Coterminal angles are angles that angles that share the same terminal side no matter how many revolutions you do. So if I continued another full revolution and I ended back right here again, another 360, then that's a coterminal angle. So 295 plus 360 gives me, what is that, 655? 655 degrees is a coterminal angle for this guy that we're referring to. That's a positive coterminal angle. A negative coterminal angle, you could consider, I guess, going backwards then, right? If I went forward, if I went counterclockwise this way to get to 295, I could have also gone backwards this amount. How far away is 295 from 360, I guess is the question you're asking. So 295 minus 360 gives you the negative version of what it is that we're looking at. That is 65 degrees, negative 65 degrees. So this guy here is what we're looking at. Subtracting 360 from 295, and negative 65 degrees is coterminal with that. That's it. Number 32, let's do the same thing with these with this radian measure. Now, I want to stick in radians as long as I possibly can. I might speak in terms of degrees, but I will not do an actual conversion if not needed. One thing to consider is how many times this is revolving around circle-wise, right? Now, we are going backwards in this case because it's a negative measure. Well, right here, if I go full circle around, I've gone negative 2 pi radians so far. So this is negative 2 pi radians, which over 15, that's negative 30 pi over 15. So I've gone this far so far. If I continued to go another full 2 pi radians around, I would have gone past negative 53 pi over 15 because this would have been negative 60 pi over 15. So how much more do I need to subtract from here to get to here? It looks like another 23 pi over 15. So here's an equivalent to what it is that we just wrote. Now, how come I did 30 pi over 15 in the first place? Because that is one full circle. So that 2 pi right there. And don't worry, I'm going to be subtracting and stuff as well. Now, I'm showing you where it is that we're at because what I can also do is I can also add 2 pi again from this value right here. So adding 30 pi over 15. And you get the equivalent, over 15, and you'll get the equivalent of what we were just previously looking at. This guy and this guy are the same thing. Okay, they're the same thing because this is another 2 pi units closer to 0. So that's a negative coterminal angle. Let's get a positive coterminal angle. Let's add another 2 pi from this value. That's another 30 pi over 15. So that's going to be 7 pi over 15 right there. That's a positive coterminal angle. So this, So this is equal to negative 23 pi over 15. And also positive 7 pi over 15. And I'm sure you could get a whole lot more than just that. But adding and subtracting 2 pi, right? Or just adding 2 pi twice. I added 360 and I subtracted 360 from here. So it just depends on what measure you're in. Find the exact value of each trigonometric function. Cotangent of this theta right here, if you're negative pi over 4, and cosine of this theta, if you're negative 2 pi over 3. Okay, this whole thing runs with right triangles here. What you're going to do is find out where the terminal side meets an altitude with the x-axis here. Draw an altitude straight up to that x-axis and you create a right triangle. That right triangle has 3 angles in it. The right angle, this far angle out here, and the central angle, meaning the angle formed from the center. This is equivalent to the theta that we're referring to right here. Now I'm going to be using degrees in this case, or I'm going to convert pi over 4, in this case 2 degrees. When I went down negative pi over 4 units, I went down 45 units. That means this angle measures 45. When I take the cotangent of this very specific 45 degrees, I'm going to be looking at the side ratios that we're referring to right here. In a 45, 45, 90 degree right triangle, both of the legs are of length 1. Now keep in mind, this will be a negative 1 because we're going down. And then the hypotenuse in relation to that is root 2 times larger than those two. So this is 1 to 1 to root 2, and of course this is negative right here. So this specific cotangent of 45, which by the way is adjacent over opposite, that'll be 1, this is adjacent to that angle here, divided by negative 1, which is negative 1. So if you're in your calculator and you type, even though this is the non-calculator portion, if you type cotangent of 45 degrees, cotangent of negative 45 degrees, really, or cotangent of negative pi over 4, you will be getting negative 1 as your value. Okay, this is the same kind of problem, only now we're doing cosine here, and we have our triangle drawn in a different place. Still altitude to the x-axis from the end right here. We create a right triangle. This right triangle has this right angle, this angle, which I'll never really do that much of, and this central angle. This central angle, don't go just by the drawing. I can tell you a little bit more about how far we went here in just a moment, but this central angle is 60 degrees, while this will be 30 degrees. Now, besides just looking at the drawing and say how I knew, let's kind of take a look at this negative 2 pi over 3. Negative 2 pi over 3 is the same as negative 2 times 180 over 3, at least in terms of degrees. Negative 2 times 180 is negative 360. Negative 360 divided by 3 is negative 120. So I went 120 degrees this way. So here's 90 degrees. Here's an extra 30 degrees right here. All that's left to get this 180 is another 60. So that's one way of knowing that that's 60 degrees, besides the drawing, of course. Okay, now why do we do that? Because we're going to be taking the cosine of this very specific 60 degrees, which happens to have an adjacent side, opposite 30 is this 1. Now it's negative because I'm going to the left. Opposite the 60 is root 3 times larger than the side opposite 30. And of course this will be negative as well because we're going downward. And then the hypotenuse is twice as large. You might have noticed that my hypotenuse has not been negative both times, despite the fact that it's kind of written downward. Hypotenuse will never be negative. It'll always be positive. So let's find the cosine of the 60 degrees right here. That's adjacent over hypotenuse, which is negative 1 over 2, or negative 0.5. So once again, you can try and type that in your calculator. You'll be getting that as well. The important thing to note right here are your special triangles and their ratios. So if you understand that 30, 60, 90 has 1 to 2 to root 3 kind of special triangle relationship, and as long as you know where you're at, sign-wise, that's good. If you do not remember to do these signs here, and you are uncertain whether you know what the signs are, remember this mnemonic device right here. All students take calculus. All students take calculus. What these letters represent are abbreviations for sine, cosine, tangent, and all. What this says is in the first quadrant, whether you take the sine, cosine, or tangent of an angle measure that is represented within the first quadrant here, no matter what, all of them will be positive. That's also true for cosecant, secant, and cotangent. When you take sine or cosecant in the second, now cosecant's the reciprocal of sine, that's why I'm writing that. In the second quadrant right here of an angle measure in the second quadrant, only this one will yield a positive result. Cosine and tangent will not. Likewise, tangent down here, or cotangent, will be the only one that gives you a positive result here when you apply trig function there. That's why when we took cosine right here, it was negative, because only tangent will give you positive. And last one, cosine right here would become positive. So we tried cotangent here, or secant. So we tried tangent, cotangent down here, and that is not cosine or secant. So that one did not work either. Only cosine values would be positive here. So if you know that much, then I could say, all right, for here I could just take the tangent and it could be positive 1/2, or cotangent is positive 1/2. Okay? And as we do positive 1/2, we say, wait, but only tangent, cosine. Cosine positive 1/2, and say, wait, only tangent can be positive, therefore this one would be negative. So that's another way of looking at that. Number 35, find the value of the trig function indicated. So all they're asking you to do is write out the ratio. Now, if the fraction can be reduced, please do that as well. Cosine of theta, that is adjacent over hypotenuse. Now, we don't have the length of this side right here. You could determine it through Pythagorean theorem. In fact, this would be 9, but I don't need that one right here. Here's my angle. Adjacent to this angle is the 12. The hypotenuse of this right triangle is 15. So it's 12 over 15. That does reduce to 4/5. We are not going to write this decimal equivalent, but if you tried to type something to make that happen, you'd also get 0.8. This is the best answer you could be writing here. Not this, not that, even though they're both exact and the same. Find the exact value of the trigonometric function, doing kind of the same stuff we did before, only now we have some revolutions to consider. Okay, negative 675 degrees. We are going a full 360. Not a full 360 again, because another full 360 would be 720, right? So a little less than that. How much less than 720 is 675? So let's do 720 minus 675, and that'll determine, that's 45, how far we're going up in this direction. And that's important, because this central angle is going to be used. Why? Because we are once again going to draw an altitude to our x-axis, not the y-axis, just the x-axis, from here. I'm looking at a 45, 45, 90 triangle. All my 4s always turn into 9s somehow. A 45, 45, 90 triangle. Anyway, that's a 45. And the relationship is 1 to 1 to root 2. Okay? Now, all of the trig functions I do in the first quadrant will always give me positive results, because this goes to the right, this goes up, and hypotenuses are always positive. Nevertheless, we know that from all students take calculus. So when we take the cosecant of this guy right here, which, by the way, cosecant is the inverse, the reciprocal of sine, so it's going to be hypotenuse over opposite, we'll be getting root 2 over opposite this 45 right here is 1, which is root 2. There's an exact value for that thing. Exact value. Secant of this theta right here, this angle measures negative 630 degrees, full 360, with another 270 degrees right there. And we're left up at this 90 degree angle measure. Now this particular 90 degree angle measure, it is 90 degrees, but it doesn't give you a triangle anymore. But I will still talk in terms of triangle stuff. What I mean by that is, let's say we had a very, very, very skinny right triangle right there. Okay. If I were to take the secant of this guy, which, by the way, is hypotenuse over adjacent, because it's the reciprocal for a cosine function, okay, Notice what's going to happen with this adjacent guy as it starts to close in closer to this 90-degree angle measure. Your adjacent value will be 0. It will be gone. Your hypotenuse can be whatever it needs to be. In this case, we can refer in terms of a unit circle. The hypotenuse would be considered to be 1. Same with the opposite. It would also be 1 because it would be this guy right here closing up on that line. So hypotenuse is 1. Adjacent side is 0. 1 divided by 0 is undefined. So there is no exact value for this one. Exactly so. Try and take the secant of negative 630 degrees in your calculator. Make sure that your mode is in degrees, and you can confirm that. Although, of course, this was the non-graphing calculator stuff, but I think I'm about to jump right into the graphing calculator stuff. So if you're ready, I am. Okay, describe the end behavior of each function. Now, you do get to use your graphing calculator. I will use it only for problems that I have to. Okay? This problem, I do not have to, so I will not. Feel free to use yours to check on it. X to the fourth plus x cubed minus 3x squared minus 1. The only two things I need to know for this problem are whether this leading power is even or odd, and what the sign in front of this guy is, positive or negative. Okay? Now the leading coefficient is a positive 1. The 4 is an even value. A positive, even-powered function will always be coming from the top. It might do some funny stuff right here, but it's going to finish up at the top going to the right as well. So your notation for this stuff, you could say as x goes to the left, your function is increasing. As x goes to the right, your function is increasing. This is end behavior. This is stating what happens at the very end. It might hit some relative extremes, such as going down, then going up, then going down. But in the end, it will result to be going up all the way. All even-powered functions start up, finish up, or start down, finish down. If it's odd-powered, it would start down, finish up, or start up, finish down. How does an even-powered function start down, finish down? If this was negative. If it was a negative 1 right here, it would be looking more like that. Okay. Maybe it doesn't have those little humps in the middle, but it will start down and finish down. That's the point. So let's write this in that notation here. As x goes to the left forever, your y value is increasing. It is approaching positive infinity. And as x approaches positive infinity, going to the right, it is increasing on that side as well. Okay, now that's the appearance of that notation. Left increasing, right increasing. Okay, next one right here. Same thing as before. These things really don't matter. In fact, you could cross them out and ignore them completely. This is an even value. This is a positive value. And this is an odd exponent. Odd-powered function can either look like this or like this, okay? Starting from the bottom, finishing at the top, or starting from the top, finishing at the bottom. It will be, when positive, it will be this one right here. So as x goes forever in the left direction there, your function will be decreasing, and as it goes to the right, it will be increasing. And of course, you can plug in values to try that, especially with your graphing calculator, or better yet, you can graph this with your graphing calculator. So you're going to be able to have some looks for that. So as x approaches negative infinity, your function is decreasing as well, approaching its own negative infinity for y. And as x approaches positive infinity, your y value, f of x, is also approaching positive infinity. There you go. Cool. Sketch the graph of this function, which of course you can use a graphing calculator. I will refrain. I did mention how to do most of this kind of problem in the other, the non-graphing calculator exponential graph that kind of reminded me of this one right here. So if you want to look at more explanation, please go ahead and take a look at that one at any time of your choosing. I will begin with the asymptote, horizontal asymptote, if you will. That is at y equals 0. As x increases without bound and gets incredibly large, your y value gets super close to 0, but never actually becomes it. So I place my asymptote right there. Okay, every other point after this here, let's see. Let's find points on the graph. X equals 0. 1/3 to the 0 power is 1. Times 2 is 2. Or times 2 is 2. When x is 0, y is 2. Every time x increases by 1, I get 1/3 times closer to this asymptote. 1/3 of 2 is 2/3. 1/3 of 2/3 is 2/9. And 2/27, etc. gets too small. Divide by 3 going this way, multiply by 3 going this way. 2 units away here, 6 units away right here. 6 units away right here, 18 units away right here. This is once again another decay rate of 1/3, and it's going down. Let's just go like this. It's going down farther and farther and starts to kind of decrease. It's a sharp turn right there. It'll never cross that blue. It'll only approach it like so. Okay. Use your graphing calculator to confirm, of course, or to graph it. Identify the domain and range of each and then sketch the graph. Okay, so just like the log function that I graphed before, I'm going to go pretty quickly with this, all told. Domain is probably the first thing you want to start with anyway because it helps you for your vertical asymptote. I cannot take the log of 0 or a negative number, so my x minus 1 value has to be positive. It has to be greater than 0. If that's the case, x has to be greater than 1. The range is all real numbers for all logarithms. Range is all real numbers. So for all basic logarithms. So x equals 1 is my vertical asymptote right here because it can't be 1 or anything less than it. If I remove myself 1 unit away from the vertical asymptote right here, I will be taking the log of 1. Notice this is 2 minus 1, which is 1. Log of 1 is 0, no matter the base. 0 minus 3 is negative 3. So when I'm over here, I'm down 3 units. There's a point on my graph. Because you take the log of something and you get a y value out, your y value kind of represents the exponent in this case. Every time your y value increases by 1, your exponent increases by 1, and your base gets multiplied by another power of 4. So if this is 1 unit away, right here, then the next one as y increases by 1 will be 4 times farther out than the previous amount. The next one will be 4 times farther out again, which is like 16, which is like way out there, way off the graph. So kind of too far out. If I multiply by 4 going up, then I'll divide by 4 going down. This is 1/4 and 1/16, and just too close to do anything with. So this graph right here, which I will never draw really good curves on these, I'm sorry, looks like that. Of course, use a graph to confirm. If you do, understand that you would be graphing it possibly like this. Log of x minus 1 divided by log of 4, all minus 3. This is the equivalent. This will give you that graph. Number 5, use a calculator to approximate each to the nearest thousandth. Okay, so this goes right back to what I was talking about before, just last time. I can do log of 2.1 divided by log of 5. Now I am going to use my calculator that I have right here to make this one actually happen. So we get, let's see here. Let's turn it on. And we're looking at log of 2.1 divided by log of 5. Okay, 0.46099, etc. Nearest thousandth, so nearest 3 decimal places. So this is equal to, let's see here. So this is equal to approximately 0.461. Number 6, solve this equation. The log of 7 minus the log of 5x equals 1. All right. I would try and combine these logs if I can. If you have multiple logs, it's going to be a harder issue to eliminate them. So how do you combine these as one log? Well, this is the log of 7 over 5x, because subtraction of 2 logs here is the quotient of, written as a fraction, numerator, denominator within one log right there, equals 1. Okay, what to do next right here? Well, you have to know what base you're referring to here. This is base 10. If it's not written, then it is, right? So in exponential form, this would be 10 to the first power equals 7 over 5x. All right. Multiply both sides by 5x there, and we'll get 50x equals 7. Divide, we'll get x equals 7 over 50x. 7 over 50. Okay. I don't know if they'd say to the nearest thousandth or not. Probably not. But this thing is, what, 0.14 exactly? I think that makes sense there. So exactly 0.14 units. Just double check and make sure that it doesn't give you 0 or a negative number when you plug it in at any one point. It doesn't look like it will. You just want to make sure you just do not take the log of a negative number in any case, right? It's only hurtful to end up doing that. It doesn't end up helping you very much because there's no solution in that case. All right, identify the domain and range of each. Okay, so first of all, range is going to be all real numbers. I've already mentioned that before. That's for all logarithmic equations, just like how the inverse, its exponentials, have a domain of all real numbers. The domain is once again saying that this guy that I take the log of has to be greater than 0, has to be positive. 2x plus 6 is greater than 0, so 2x is greater than negative 6, so x is greater than negative 3. That's your domain. Anything that's greater than negative 3 will give me the log of a positive number, and all will be fair. All will be good. Make sure I don't have to evaluate. Okay, so nothing else there. Awesome. Okay, graph this function. Okay, I'll do a little bit with you here, and then if I want to go to the calculator, I feel like I might. We'll see. So negative 3x over x minus 2 right here. What I'm going to begin with, what I did from the previous ones, I think I started vertical asymptote. Okay. This domain restriction says I have to make sure that my x minus 2 is not 0. So x cannot be 2. So the vertical asymptote is x equals 2, because that's where your points don't touch on this line right here. Okay. Vertical asymptotes there. Now let's check for x and y intercepts should they exist. Let's find y-intercept first, set x equal to 0. We get 0, the opposite of 0 over 0 minus 2, which is negative 0 over negative 2, which is 0. So your y-intercept is at the point 0, 0. How fascinating. Which means there's an x-intercept also of 0, 0, of course. Let's see if there are any others. And if not, then that's the only place it goes. So let's see. Let's take the f of 0 and figure out what y becomes when x is 0 for the x-intercepts. Excuse me, we just did that. Let's substitute 0 for y and figure out what x would have to become. Divide both sides by negative 3. X equals 0. Looks like that's the only one as well. So also 0, 0. So we have these points plotted. We're good to go. Okay. Now what's left is to see, is there any horizontal asymptote, slant asymptote, anything like that? What else can we graph? Any other plots we can, or points we can plot? If you want to find the slant asymptote very easily, just go ahead and divide this outright, meaning make sure that you longer synthetic division right here. I'll go ahead and do synthetic. We're going to do negative 3x over x minus 2. And your root, in this case, is 2. Okay, your linear guy is negative 3. Your constant guy is 0. So let's apply synthetic division to this. And we'll be ending up with the following. F of x equals negative 3. And here's the remainder, minus 6 over x minus 2. So this helps you identify what your horizontal asymptote is. Your horizontal asymptote represents this guy right here. Because, one, it's constant. That's what makes it horizontal instead of a slant asymptote if it was linear. And 2, this remainder can never be 0, so you'll always be adding or subtracting something from this value to get a value for y, which means you'll never be negative 3, meaning y equals negative 3. You will only be any other value other than y equals negative 3 in this case. There's your horizontal asymptote. Okay, every point that I really do from here does have to do with this remainder. It's how far up and down I remove myself from negative 3. As x increases by 1 or decreases by 1 going left to right. And this is how I would do it. every time I move 1 away in this direction, I'll be doing negative 6 divided by the number that I'm moving away from. In other words, when I move away from 1 right here, that's at x equals 3. 3 minus 2 is 1. All right? Negative 6 over 1 is negative 6. So when I move over 1, I'll be doing negative 6 over 1. 1, 2, 3, 4, 5, 6. So what I'm going to do is I'm going to move over units that I can divide 6 by. 2 units over. Negative 6 divided by 2 is negative 3. 3 over. Negative 6 divided by negative 3 is negative 2. Can't go 4 or 5 over without having some fractions. 6 over. Negative 6 divided by 6 is negative 1. I think that's enough points there, at least to fit on this graph here. There we go. This side right here, 1 over negative 6 divided by negative 1 is positive 6. Negative 6 divided by negative 2 is positive 3. Negative 6 divided by negative 3 is positive 2. See, it's always good to have this point and say, see, we still landed on the same point. I can confirm that this works. Negative 6 divided by negative 6 is positive 1. If I wanted to try and reach some more points, I could divide by 12 and I'd get 1/2. It's not my favorite fraction. Well, it's probably my favorite fraction in the world, even though unfortunately it is a fraction. So if you're going over 12 here, what if you went over 1/2? Negative 6 divided by negative 1/2 is positive 12. So this would be jumping way up here, right? You could use that as well and get that point. So I got a bunch of points here. Again, confirm with your graphing calculator. I did not use it for this particular instance. However, you can when it comes to using a calculator on test. And of course, multiple choice. Just look for the one that has the correct asymptotes and anything else involved. With negative rational functions, you'd be looking at them on the top left and bottom right. Positive rational functions, you'd be looking at top right and bottom left in basic form like this. Anyway, this stuff helped me find all my other features. Number 9, we have an exponential function here. We got to solve the equation, round our answer to the nearest 10,000th. Looks like we will have to use our graphing calculator to just find our final answer here. So I'm going to begin by adding 10 to both sides here. This negative 10 is not really helping me do what it is that I want to do. 10 to the a minus 6 power equals negative 9 plus 10 is positive 1. Okay, so we are trying to find the value that, by the way, if I logged both sides here, of base 10 specifically, but if I'm looking for, 1 second, 10 to what power gives me 1? You should know that 10 to the 0 power gives you 1. So I'm just going to tell you right off the bat that this a minus 6 is 0. But, you know, if you're stubbornly and blindly going through the problem, you might have this set up here. Log base 10 of 10 is 1. This a minus 6 power gets to multiply in front of log base 10 of 10, which is 1. So a minus 6 times 1 is a minus 6. Log base 10 of 1 says 10 to what power is 1, which is kind of what we've been asking before. That value is 0. And of course, you can use a graphing calculator to figure that out. Add 6, we get a equals 6. Okay, to double check, 10 to the 6 minus 6 is 10 to the 0, which is 1. 1 minus 10 is negative 9. Pans out. A equals 6. Okay, these are the last 3 problems of this whole thing. Find the measure of each angle indicated, round to the nearest 10th. Okay, this right triangle, and I'm just going to tell you this right now. I've taught enough classes to see students make this mistake all of the time. They say, this is your hypotenuse, here could be A and B and everything else like that. Meaning they'll do opposite over hypotenuse, meaning they'll do sine, okay? This is not your hypotenuse. Take a look where your right angle is. So, my recommendation, do not fall into this trap, please. My recommendation, redraw the right triangle so that the base is somewhere on the ground. Don't just say slants are hypotenuses. Absolutely not. This is your hypotenuse in this case, this AB. In fact, rewrite where some things go now. Right angle's here. Looks like A is still over here. C is with the right angle. B is up here. Between B and C is the value 6. Between A and C is the value 16. Your angle theta is at angle A. All right. Now let's find the measure of the angle based on what we have there. Okay. In relation to A, we know the side opposite. we know the side adjacent. So we should use probably tangent or cotangent. I'm just going to go ahead and use tangent here. The tangent of theta is 6/16. If you'd like, you may reduce this fraction right here. It won't help or hurt. But if you like the smaller numbers, please go ahead and do that. 3/8. And even if you know that measure, well, once again, you can use the calculator, but even if you know that measure exactly, that is 0.375. So just, if you try this way, go ahead and confirm that you get the same answer no matter what we do with this. So the tangent of theta is 0.375. That is the ratio. This is the opposite over hypotenuse that gives you that. Meaning if you take the tangent of some angle measure and get 0.375, what was that angle? Do not start typing in a bunch of angles until you get around here. There is an inverse function that you can use for tangent, and it is called inverse tangent. If you take the inverse tangent of both sides, on this right side here, take the inverse tangent of a ratio, you get an angle measure back out, theta equals. We are about to find that right now. Now, the only thing with this that you have to also be careful of when we do this is make sure that your mode is in degrees and not radians. Well, actually, I take that back. Make sure that whatever you get it in, that you indicate the units. But I would prefer to do degrees for this. When you round to the nearest tenth and we're trying to find the measure that, we look at radians with pi. And if this thing isn't written as like 2 pi over 3 or anything like that, it's just best that we use degrees unless they ask us to use radians. So I'm in degrees, okay? Quit out. Let's take the inverse tangent of 0.375. Where is this button? Well, it's above the tangent button, so it's the second right there. 0.375. If you want to try and do 6/16, please go ahead. We'll get the same answer. Or 3/8, please go ahead. We'll get the same answer. So right here, we get this value, round to the nearest tenth. So this is rounded. Whoa. Rounded, we will be getting. How do I hide this calculator? There we go. Rounded, we are looking at, I don't want to hide it. What was it? 20.55, so 20.6 degrees. There's my theta. Find the measure of each side indicated, round to the nearest tenth. Once again, just for consistency's sake, let's get this right triangle redrawn this way. Get the base on the bottom. By base, I mean with the right angle. This can be A still if you'd like, and that'll be C, and then B can be up here, where we now get 38 degrees. The hypotenuse is 10.6 units, and between A and C is our unknown x. Okay, we know that this thing's 38 degrees here. We know that, or we don't know the side opposite that we're trying to find. We do know the hypotenuse. So let's go ahead and use sine here, opposite over hypotenuse. Sine of 38 degrees equals x over 10.6. Do not round this number early. Leave it exactly like that until you're ready to write x equals with an exact value. And what should we do? Multiply both sides by 10.6. This is what x is going to equal. 10.6 times the sine of 38 degrees. Now, knowing that we are in degrees right here in the problem, make sure that you're in degrees on your calculator, which we are. So we're going to be doing 10.6 times, looks like I missed the 1, 10.6 times, that's a plus, just testing you, the sine of 38 degrees. And this will give me an approximate value. I'll show you different ways we can double check this. Whoops, I did something wrong. Let's try that again. 10.6. It might have messed up on the last problem there. Times sine of 38. Okay, 6.526, etc. So let's go ahead and round that. Okay, that's about, whoops. That's about, let's see, 6.5 units. Okay. Here's the main double checking measure that I'm going to do. X is a leg, 10.6 is a hypotenuse. Okay. This should be less than this right here. And not necessarily significantly less, but it should be less. If you got an answer of 12 something, I don't know what could have gone wrong. If you got an answer of 12 something, there's something wrong with that because this is a leg, this is hypotenuse. It should definitely be shorter. Good double checking measure there. Last one, find the measure of the indicated angle to the nearest degree. Same kind of idea. In fact, let's use a variable in the place. Let's use theta. Okay. This one's drawn kind of the way that I'd like it to. We know the opposite of it. We know the hypotenuse of it. So let's go ahead and use sine. The sine of theta is opposite over hypotenuse. Okay. I am going to go ahead and reduce this fraction like I like to. Both of these, 5, 8, let's see, I guess it's 2. Divided by 2, we get 9 over 20. So that's as best as it can reduce to as a fraction. This is an exact decimal, which is 0.45. I'm going to use that one just to do it. There's no other reason. Other than if you want to double check, here, how about this? If you want to double check, you take the sine of something, your calculator will give you that value. I know you can convert it into fraction form, but I'll play with this. You can play with 18 over 40. Now the sine of the angle measure is the ratio, so the inverse sine of the ratio gives you the angle measure. Inverse sine both sides right here, we will get theta equals. Make sure your calculator is in degrees as we do this. Again, one more time. This is the very last problem on this entire thing, which I'm feeling that for sure. I hope you are as well. Inverse sine of 0.45, and this will give you 26.74368395. Rounded to the nearest degree this time. That rounds up to 27 degrees. Okay. And there you go. All right. Hope this stuff was fun and beneficial, and it's kind of all I hope it was. And I hope it was productive use of your time there. Fiend!